Hello everyone, welcome. Today we'll discuss a recent paper called a comparison of discrete and soft speech units for improved voice conversion. And this paper came out around a month ago, and this paper is a collaboration between Ubisoft LaForge and Stellenbosch University. These are the authors. The tutorial will cover first the overview of the paper, then we'll see the proposed approach, then we'll see the experiments, and finally we'll see some results. Before diving into details, let's understand what is voice conversion. So the idea of voice conversion is very simple. Let's say you have a input audio. Let's call it as A or A1, and the audio will have some speaker S1 and some content C1. So when I say speaker, let's assume some speaker like for example Obama, right? And content C1 is what Obama speaks, right? For example, he says she had your dark suit in greasy washout all year, right? So that is a sentence spoken by Obama. And what we want from voice conversion system is to output the same content, which is she had your dog suit in greasy washout earlier, but spoken by some other speaker S2, right? So the content is same, right? So content is C1, but the speaker changes, right? So that's why it's called voice conversion, or probably you can call it a speaker conversion, right? And as I said, so it's about transforming a source speech into a target speech or target voice by keeping the content same, right? And that's the idea of voice conversion. And there are various ways to do this task, right? One simple way, one simple approach you can use is the cascaded system or cascaded approach, where you can first feed your audio from speaker one into a speech recognition system, which will give you a transcript, right? So because speech recognition systems are speaker agnostics, right? And the transcript, you can use it, right? So let's just write it here. So we have cascaded system where you have ASR, and then you feed the ASR output to a TTS engine. And TTS engine, as you know, always produces one speaker, assuming you have single speaker TTS. If you go for multi-speaker TTS, you may get more, but assuming you have single speaker TTS, if you feed the output of ASR to the TTS, you will get the content which is produced by ASR model spoken by some speaker, some fixed speaker, right? So this is the cascaded system, and this people always use it as a baseline, and people want to improve over this cascaded system, because usually ASR will give you some transcript errors, and those transcript errors will get propagated into the TTS engine, and so the output will always be not always, sometimes will be erroneous, right? We don't want that, because we want to keep the content same. Whatever is spoken by speaker one here, we want to keep it exactly in the output of the VC. And only thing we want to change here is the speaker, right? So seems like very simple problem, right? Like it's just changing the speakers, right? Just like we change prosody of the audio, for example, right? So there are various ways to change the prosody of a audio signal, or the pitch, or there are various things, or features in speech. For example, the timbre and the phonaut feature and so on. So those all we can change. We know like how to change those using prosody synthesis modules. But here the idea is to change the speaker, the speaker ID basically. So it seems like it's easy problem, but it's not really a easy problem to solve, right? And like I said, there are various way, and one simple baseline could be this cascaded system, like I just told you. And we'll see in this paper also uses this cascaded system for their baseline. And the specifically this paper explores something called self-supervised speech representation model for voice conversion. And as you guys know, self-supervised models these days are becoming very hot. And like for example, wave-to-wake, Hubert, and there are many self-supervised models these days in speech. And so the idea of this paper is to explore those, and they also show that they also explore something called discrete speech units and soft speech units as input features for the VC system. And we will see what are the advantages and disadvantages between these two units. And they, as you can see here, it's already written. So discrete representations effectively remove the speaker information but discards some of the linguistic content. So that kind of gives you leads you to the mispronunciation of the audio or mispronunciation of the phonemes, right? And so this paper proposes something called soft speech units out of this Hubert model, and they show that kind of in between, that's sort of in between the discrete units and the just raw features which you get from the self-supervised models, and they show that this is kind of very good for this particular problem. So let's look at the proposed approach. As you can see here, there is the first part here is the content encoder, which is kind of takes some raw audio and encodes it into some high level features, right? So let's we will see like what you will get out of this content encoder. So it could be this or it could be this, right? And output of this content encoder goes into acoustic model and vocoder, which is the standard text-to-speech engines blocks. So that acoustic model takes phonemes or graphemes, usually like in the olden style. So basically, it takes some phonemes or graphemes and then creates spectrograms. And from spectrograms, you can create raw audio using the vocoder, right? And so that is the whole block here, right? So you have audio fed into content encoder, which extract features which don't have any speaker information. So let's just say that whatever you get here will have no speaker info, right? And and that goes as input to the acoustic model, and then you have vocoder generate the audio of that particular of this input representation, right? So as I said, so the output of content encoder could be two things. One is the discrete content encoder, which gives you the discrete units, which are shown here, D1, D2, DT, and so on. And this discrete units, you can get it from, you can get in different ways or different features. For example, you can just feed your audio to the content encoder, and the feature extractor could be, as I said, could be some large self-supervised models like Wave2Vec 2.0, right? And the feature extractor is basically the content and the content the context network, and the context network output are these for example the 1024 dimensional feature vectors, the continuous vectors. You can feed them to a k-means cluster, and the cluster, and you can specify how many clusters you want, and the k-means cluster will do clustering, and you can just take the centroids of these clusters and define them as the discrete speech units, right? So it's as simple as that. Now you got this discrete speech units. You can feed those into the acoustic model, and then you can generate the audio for these discrete units. This is a very simple way, right? So it's a straightforward method. So in case of cascade system, what do we do? What we do is we generate the text directly, and then we feed that to the acoustic model and vocoder. Whereas in this case, we want to join the self-supervised models, which will have some high-level representation of the phonemes, right? And those phonemes representations we want to feed it to the acoustic model. So we're not exactly feeding the phonemes, but we are actually feeding. This could be phonemes. I mean, these are discrete. They can be phonemes, but we don't know. We can't label them, right? Unlike in case of English, we have 46 phonemes, right? So we know what those phonemes are, at least in IPA symbols. But in case of this, we don't know what those phonemes or what those symbols discrete units represent. We don't know if they are really phonemes, right? So those will go as input to the acoustic model. So this is like a different way, right? Not exactly like how people used to train text-to-speech engines, right? So that is one way, straightforward way. But this doesn't seem to work quite well, and like I explained the reason before. So what they are proposing, or in this paper, what these guys are proposing is to come up with some speech units which are in between discrete units and continuous representations directly from the self-supervised models. So how do they do that? So very simple. You feed your audio to a backbone network or feature extractor, which will give you some high-level representations, right? S1, S2, and so on. Sorry, not S1, S2. Whatever you get here, like 1024 dimensional feature vector. Then you feed them to a linear projection layer, which will kind of project these high-level or high dimension feature vector into low dimension vectors. For example, S1, S2, and so on, right? ST. Then you can use a softmax over these and then get the indexes of the discrete speech units, right? Very simple. So that's why they call it soft content encoder. So basically, the idea is very simple, right? You feed the features vectors from the backbone network to or a feature extractor to a linear projection layer, and then you do just apply softmax over those vectors or softmax over those speech units. As simple as that, right? Now, so given this, let's understand what I mean, I already explained what these are. Let's just go over those concepts one more time. So, discrete content encoder. Again, as I said, you just feed your audio and get the feature extraction from or features from the feature extractors, and then apply k-means, and you will get these discrete speech units, D1, D2, and so on, right? And as I said, there are various ways to various features you can use to the for the k-means clustering module, such as you can use simple MFCC, which usually don't work, and or you can use self-supervised speech representations from CPC model or Hubert and so on, right? Then you have soft content encoder. As I said, it's very simple. You take the features from the feature extractor, and then you feed it to a linear projection layer and then apply softmax. Right? That's like here. Now, for acoustic model and encoder, which is the text-to-speech block. So, they are using a simple Tacotron 2 model, which basically takes some inputs such as graphemes or phonemes, but in our case, we are feeding the soft speech units and applies or generates MFCC, spectrogram or MFCC or spectrograms, right? And those spectrograms will be fed as input to the vocoders. The vocoders could be models such as WaveNet or iFigan, which are which gives you very high quality audio. That's called vocoder, right? So and after that you have your audio, right? So very simple. So just to summarize, you take your audio, which is from source, and then you feed it to the content encoder, and from the content encoder you feed it to the acoustic model, which is the Tacotron 2 model, which generates the spectrogram, and the spectrogram you feed it to a vocoder, which is in our case it could be WaveNet or HiFiGAN, and that generates the waveform. So let's look into the experimental setup here. They are using LJ speech data for training all the models, and they check or they compare the discrete and soft speech units across two tasks: intra and cross-lingual voice conversion. Intra means the presentation, the self-supervised models will be usually trained on English, and if you use only English if you use English, which is the LG speech data, that becomes intra because your representation model is basically has learned the English phonemes, and also cross-lingual means you're using the same model for for different tasks, different language, which is called cross-lingual. And intralingual conversion is libre speech declined as a source speech, and for cross-lingual they use French and Afrikaans data, which is CSS 10 data set. We'll see the results and everything, and if you want to know more about the data set, please Google. And coming to the experimental setup of the models, they're applying k-means clustering from the intermediate representation from the CPC big and Hubert based models, and they use 100 clusters in order to estimate their means on subset of 100 speakers. And CPC big, for CPC big, the outputs from the last or the second LSTM layers in the context network is used for feature extraction, and few more normalization and few other steps are done for features for to extract the features. And for soft content encoder, they use CPC big and Hubert base as backbones, as I said before, and we fine tune each model on libre speech and to predict the corresponding discrete phonemes. That makes sense. And the training is done for 25,000 steps using the learning rate of this 2 × 10⁻⁵. And coming to the TTS model, as I said, the TTS is based on Tacotron 2. If you want to know about Tacotron, if you want to know more about Tacotron 2, I have a video, or you can read the paper. It has encoder and decoder kind of structure, sequence model. And as I said, the input is the soft speech units, which goes as input to the encoder, and the decoder generates the spectrogram, and the spectrograms are fed as input to the vocoder, which will generate the audio waveform. And they use hi-fi GAN in this setting to generate the audio, or to generate the raw waveform. Seems to work really well. And the acoustic model and vocoder are trained on LG speech, and so that some data processing or pre-processing is done on the data set. They downsample the 22 downsample the LG speech data to 16 kilohertz, just to match it with the self-supervised models, which is again trained on 16,000 or 60 kilohertz sampling rate. And then for Mel spectrogram, they use 128 band Mel spectrograms, hop length and window size, as you can see here. And acoustic model, which is the TTS, is trained for 50,000 epochs, 50,000 steps. And then for hi-fi GAN, they first use the ground truth spectrograms for 1 million steps, and then they fine tune it with predicted spectrogram for 500,000 steps. Coming to the results, they have different methods or different metrics to evaluate the robustness and the effectiveness of this system. First, they measure the PER, which is the phoneme error rate. Lower the better. Then you have WER, then you have ER to measure the similarity of the speakers. Then you have Mohs score, which measures the quality or the understandability of the it's basically it's a score, which is basically higher means better. It's the quality is better. So basically, right. So that's the mean opinion score metric. So let's look at the results for different systems. So you can see the Hubert systems here, CPC here, and then old or previously proposed models, auto VC, cascaded system, and the ground truth. As you can see here in this section, PER, lower PER and lower WER means your audio quality is really good from the vocoder, right? Which is what we really want. We want good intelligibility, which is measured in Mohs. Sorry, again, obviously intelligibility is also measured in higher the Mohs score means good it's the quality is good, right? Intelligible audio. And as you can see, it's the Mohs score is kind of almost close to human level. Usually humans will have like 4.5 or 4.7 Mohs score. This is really good. In fact, if you listen to the audio samples which are provided in this paper, basically there's a link where you can go and see the audio quality or audio samples from these models, and they're really good. I encourage you guys to go and check out those samples. They are really good. And lower PR here, as you can see, and WR 2.6 means it's almost close to it's really good, right? The audio quality or the content you can easily it's easily similar to, or the content from the vocoder is as good as the input audio. And ER 50% means they can't distinguish between these predicted speakers, right? So that is about the Hubert method. If you look at CPC, in CPC again, if you see the soft approach, you have kind of good WR, but the PR is kind of not so great, and quality, the MOS score is not as good as the Hubert model. Coming to Auto VC, which is I think it's a 2019 paper, and the quality is not that good. I mean the PR and WRs are like worse, and even the Mohs scores are also very bad. In case of cascaded, you have okay-ish PR and WR, but the Mohs score is not so great. And ground truth seems like ground truth and Hubert soft is almost have same PR, and WR wise, the ground truth is better. They don't have ER, and as I said, the ground truth audio will have a higher Morse scores, so 4.57. That's human Morse score, right? So this is the intra-language. Coming to inter-language or cross-lingual experiment. So you have French here, you have Afrikaans here, and discrete. If you use the discrete, you will get very bad WR and PR, both for Afrikaans and French. If you use your soft, your WR improves really well, and ER it's okay. And coming to the Afrikaans, again the WR uh, goes down from 24 to 12. And in case of ground truth, you have 14.6 for French and 8.0 for Africans. And this is some breakdown of PER for per phoneme, Hubert discrete and Hubert soft. As you can see, these are some phonemes. They have Mar, and if you look at the phoneme error rates, Hubert soft is doing well, as you can see here, blue, and Hubert discrete is not so well, and they have it for all the phonemes here, right? And that's it for this tutorial. Thank you so much for watching, and see you all in the next tutorial.